Hey everybody, Mr. Piercy here, and what we're going to be looking at in this video is stuff related to the Pythagorean Theorem, but we're using the Pythagorean Theorem to introduce a new topic known as related rates. It is not something that we will do too much in geometry or even in most algebra classes. It is generally something that is reserved for a calculus course. But this is a good lesson to introduce the concept and to reinforce things that we know about the Pythagorean theorem. Now, the lesson itself is asking you to take a pre-measured stick that is 13 centimeters long and place it up against a wall. And it looks kind of like the diagram that we see down here in the bottom, where you start with the stick up against the wall, so you don't even have a triangle really. And then every 10 seconds, the bottom of the stick moves 1 centimeter further away from the wall than it did the first 10 seconds. So this is something that you can do without having to actually measure it. You can just do it on paper and get the values that you would need. The only thing that we won't be doing is actually measuring the height that the stick goes up the wall. The lesson itself is asking you to measure the distance that the stick goes up the wall. So here, if it's sitting on the wall, it goes 13 centimeters up the wall. Well, now we are creating a right triangle where this is 13 centimeters and this is 1 centimeter. So the distance that it goes up the wall can no longer be 13 centimeters. It has to be something less according to the Pythagorean theorem. And then we move this out so that's 2 centimeters. Well, this is still 13 centimeters. And again, you would measure this up here to see what is it. But then you still have to calculate using the Pythagorean theorem what that is and go from there. Now I want to emphasize again, like I did in the comments of the classroom, that this is a video that you should watch after you perform the activity. This is not a video that you want to watch prior to doing the activity because it would defeat the purpose of you drawing your own conclusions and thinking your way through the problems. So if you haven't done the activity yet, stop the video now and go back and work on it, and when you're done, come back and watch the video again. This is more of a recap for verifying what you should have seen and hopefully give you an opportunity to clear up any misconceptions or questions that you may have had from the activity itself. So here, part one, discuss with your partners. Now, some of you may or may not have partners to work with, but either way, you're supposed to make some predictions here. Everybody's predictions are going to be different. They may be the same as far as what they say, the message they contain, but they may not be phrased the same way. Everybody should have their kind of their own predictions here. So in step 2, part A, what type of angles are these? CAB, ABC, and so on. Well, angles CAB and ABC, those would be the acute angles of the triangle, and BCA would be the right angle of the right triangle. What specific type of angle is ABC? Well, because it has a right angle, it must be a right triangle. Specific names that we would use here. Well, segments AC and BC are the legs, and AB would be the hypotenuse. Now in the diagram that we see here, what is the length of AC and BC? AC is 5 centimeters and BC is 12 centimeters. And all we're doing is just kind of counting the centimeters that we see here. So going along the long leg, we got 1, 2, 3, 4, 5, 6, 7, and through 12 and so on. We're just kind of looking at counting the numbers from 13 to 25, and we say, oh, look, there's 12. And then from about 8 to 13, we can see, oh, well, that's 5. We're just counting those. Okay. Step 3, when it says complete the columns in the table, well, you're not going to have anything here at the bottom of the page. You're just going to go right here to the table. Now, the table is things that you're going to be doing, and I believe the file that I gave you only has, this I believe has one extra column in it, the one with the measurement. Here, the one with the measurement, we're not actually doing the measurement, so you will only be looking at the first column here, the third column, and the fourth column. So when you fill in the values, because we move 1 centimeter away from the wall at the bottom of the triangle each time, that's why every 10 seconds it's increasing by 1 centimeter. The values in the third column, where it says find the length of side B using the Pythagorean theorem, these are rounded numbers that we got using the Pythagorean theorem, and because the hypotenuse, the stick that you would actually be using, is fixed, that remains 13 centimeters throughout the whole thing. Now, using the data that we have from the table, we're going to be looking at that data as a graph. Sometimes seeing it as a graph will allow us to draw conclusions a lot easier than it would be by looking at it just as the numbers in the table. Now, here it's supposed to plot time versus side C of the triangle, which is the hypotenuse. So over time, side C of the hypotenuse doesn't change. It is 13 centimeters throughout the whole thing. So your graph should look like this. Now moving down at the questions here, as t increases, do the values of C increase, decrease, or remain constant? Well, that remains constant. It's always 13 no matter where along the time frame that we're looking at along the x-axis is. It's always 13. Well, what type of scatter plot do we show here? It's a horizontal line where y would equal to 13, or really it should say where C is equal to 13, because we're looking at the side of the hypotenuse, which is the hypotenuse of C. What is the equation of the line that best fits the data, and what is the domain? Well, I already wrote the equation in the previous answer. So you'd say y is equal to 13 or c is equal to 13, and the domain in this case is between 0 and 13 seconds. We're not going, we obviously can't have negative time, and we're only going up to 13 seconds. Or actually that should say 130 seconds. That's a typo. 130 seconds, because you're increasing by 10-second intervals. Is the length of the stick changing? No, it doesn't change. It's fixed figure. And part F, write a sentence connecting the ideas. Now, pay particular attention to how you're answering these types of questions when it says write a sentence. One of the reasons that we're doing this lesson is to verify, or is to practice how you're going to be answering questions at some point when you take an AP exam. So an AP exam is going to give you a scenario where you have to kind of use that entire scenario to kind of do what we're doing in this lesson. Be able to do a little bit of math, draw some conclusions, and ultimately form some overarching, connection here. So what I have here isn't a huge one, but it says the length of the stick is always 13 centimeters, which means, not meant, which means the graph will be constant horizontal. Now one thing real quick that I want to point out that I kind of skipped up here is right here. The graph of the data would be continuous. If you notice, I did not draw a line connecting all of those dots. And the reason why is because the data that we're collecting is not continuous. We're not taking measurements at 23 seconds or 55 seconds or 81 seconds. We're only taking data, or we're only taking the calculations, the length of the long side of the triangle, or side B, every 10 seconds. So that's why it's just those dots. If we wanted it to be continuous and we drew a line through it, that would indicate that we're taking measurements continuously between 0 seconds and 130 seconds. And in this case, we're not. So that's why we don't connect the dots here. Now we're going to look at the rate of change, and this is one of the hearts of what we're doing here. We're talking about, oops, rate of change. I don't want my highlighter anymore. We're talking, go away. Talking about the rate of change. Now remember, rate of change, in this case, delta t over, or delta c over delta t, this is what we would commonly in an algebra course refer to as the slope. So anytime you hear rate of change, you need to think, well, that's looking at the slope between 2 points. So looking at the math here, we're going to say, what it does say is if you see a pattern, you may use it to complete the table. So if I do the first two as looking at the first one as a model, the next two, I'm going to just say y2 minus y1 and x2 minus x1, and I get 0 for the interval between 20 and 30 seconds and from 30 to 40 seconds. So since the first three produces 0, the rest of these, it's reasonable to say, would also have a slope of 0, and it really does match the equation that we came up with, y is equal to 13, or c is equal to 13. It has no slope in it. And the other thing is, well, we saw the graph, it just produced a horizontal line. So here, looking at it, what is the average rate of change? Well, the average rate of change here is just 0 centimeters per second. As time increases, what happens to delta C and delta T? Well, it stays constant. And what is the change in the length of the stick? Well, what is the rate of change in the length of the stick is just 0 centimeters per second, which I guess that's what we would think of as slope, 0. Now we're looking at the data that we collected when we're looking at side A of the triangle. This is the side that moves away from the wall every 10 seconds. So when we plot our points here, from the data that we see, we get a line that kind of looks like this. And again, I'm not going to connect the dots because it's not a continuous set of data. This is only every 10 seconds that we're collecting the data, so we just leave it as a scatter plot where we're not connecting the dots. So what do we notice? As time increases, what happens to A? Well, as time increases, the value of A is also increasing. Well, what kind of line do we have? A horizontal, increasing, or decreasing line, or a curve? In this case, we have an increasing line. Again, if this particular stuff is not continuous, so that's why we don't connect the dots, what is the equation of the line? Well, in this case, the equation of the line is 1 over 10 t, and this should really say a, because that's what my independent variable is in this case. I'm sorry, yes, independent variable is time, dependent variable is the length of a as it grows. So the length of side A depends on the time. So is the distance between them, the bottom of the stick and the bottom of the wall, changing? Well, yes, it's changing, and it's increasing over time. And write a sentence. So again, here, pay attention to how you might have answered. Here, we're looking for complete sentences with appropriate math vocabulary, just like you would have done in an English class. Use complete sentences. So here I'm saying that the distance between the end of the stick and the bottom of the wall increased at a rate of 1 centimeter for every 10 seconds, giving an increasing line with a slope of 1 to 10 for 1 centimeter for every 10 seconds. Now we're looking at the third column in our table that we saw. I'm sorry, no, we're still looking. Here we're just actually calculating the rate of change between the points. So again, delta A over delta T, again, that's actually a calculus notation. Usually what they, when you see that, they introduce it to you in Algebra 1, but we see a lot of this stuff like that in calculus. And again, we're just kind of looking at the slope between the figures. And again, if you see a pattern, use the pattern. Now looking here, after I did the next two, I got a slope of 1/10, just like the first one did. So after 3 tries, when I get the same slope of 1/10, well, that to me is enough to say, well, that's the pattern. The slope is 1/10 each time. And it makes sense considering the way our graph looked and the way the equation looked. So what is the average rate of change? In this case, 1 centimeter for every 10 seconds. And as t increases, well, does that rate of change, does it increase, decrease, or remain constant? In this case, it's constant. The reason why I know it's constant is because the scatter plot produced a line. If it was not a line, then it would not be constant. That's kind of the characteristic of a line. The rate of change is always the same throughout the whole process. Is the stick moving along the ground at an increasing, decreasing, or constant rate? In this case, it's constant. Again, a characteristic of a line in math. So again, here, what is the rate of the stick moving at along the ground? Include appropriate units in your rate. This would be a very good time to kind of pay attention. Include appropriate units in your rate. That would be something that if you did, say this is, we're using this as an example for an AP question or an AP calculus exam. If you gave me the correct answer, but failed to include the appropriate units of time, well, that would mean that you're not going to get full credit for your answer here. So we have to say that it is increasing 1 centimeter for every 10 seconds. Now we're looking at the data that we collected for side B of the triangle. And here, when we graph the information that we have, we see something that looks like this. It's decreasing over time. So as time increases, what happens to B? Well, B is decreasing as time is increasing, and it's not giving me a line at all. It's not horizontal. It's not increasing. It's not decreasing. This case, it's curved. So that is going to be a clue that, well, because it's curved, the rate of change is not going to be constant throughout like it was in the previous two figures that we looked at. Is the distance of the top of the wall increasing, decreasing? How is it changing? Well, the distance is absolutely, and I don't know what is wrong with me. I could not spell to save my life, apparently, when I did this. The distance between the top of the stick and the bottom of the wall is absolutely decreasing. So as time increases, the distance from the top of the stick to the bottom of the wall is going down. Now here, write a sentence based on the ideas that you saw. So compare your answer with mine, and I'm not saying that mine is the absolute best thing in the world, but it is going to be a good representation of the type of question or the type of response that you should give on questions like this. So here the distance between the top of the stick and the bottom of the wall is decreasing, but not at a constant rate, which causes it to curve. Now here we're looking at the distance between points. Again, we're looking at the rate of change, but we have to know, well, what is the distance here? So that's why we're kind of looking at the distance formula for the change in my y values, or the change in my b values in this case specifically. Okay, and a lot of these are going to be things that you can just get from your table. It's not like you actually have to type in the square root of 13 squared minus 2 squared each time, because these are values that you could be able to just take from your points on your table. But moving to the next one, I would get a rate of change of negative 0.196. The next one would give me a rate of negative 0.708, negative 0.1378, and finally for the last one, negative 0.5. So looking at that, we can see, well, the numbers are getting bigger, which kind of matches what we saw in the table and what we wrote for our answers previously, saying that, well, the distance that it changes is increasing each time. So let's take a look at our answers here. Is the average rate of change the same between any 2 points? Clearly it is not. Why are the answers negative in this case? Well, that's a very good question, because usually we would think, well, I can't have negative numbers in geometry for my results, but in this case the negative values simply indicate the direction that it is moving. It's moving down. On what interval is the chart, the absolute value of the average rate of change, the greatest or smallest? Well, the biggest difference is between 10 and 20 seconds. Or actually, yeah, 10 and 20 seconds. No, the biggest rate of change is between 120 and 130 seconds. So that should be amended. On what interval is the chart oh, wait, I read the wrong question. The smallest, yes, this is correct. The smallest is between there, and the largest is between 120 and 130. Is the stick moving down the wall at an increasing rate? Well, in this case, it's actually increasing. Even though it's going down, and that's what the negative values indicate, that it's the direction that it's moving, the change from one interval of time to the next along that side of the triangle is it's getting bigger each time. So take a look here. These are, I think, the last questions that we have. Which rate of change always equals 0? Well, the rate of change that always equals 0 in this case was delta C and delta T, because the stick didn't change, and so the rate of change, there isn't any, because the stick is always 13 centimeters long. Which rate has a non-zero constant rate? Well, the constant rate in this case would be delta A and delta T, where it was increasing at a rate of 1 centimeter for every 10 seconds. And this part C, which rate is changing at a non-constant rate, well, in this case, that one was delta B and delta T, the one we were just looking at, because the distance that it changes, or that it moves, increases over every 10-second interval. So it's not always going to be the same. At one point it was one distance, and the next point that it changed, the distance that it moved increased. Now the whole point, again, that I mentioned about this is talking about something known as related rates. Related rates are typically something that, again, you use in calculus. It's just a way that you solve problems. But the idea of related rates is that it's a way of comparing changes in the same, figure in this case, that are not the same. And we usually compare those changes to the same quantity, and usually it's going to be time. So I would encourage you to take a moment and copy this last bit down into your notes. Again, the whole point of this lesson was really so that way we could reinforce, obviously, what we're doing with the Pythagorean Theorem, but now we can use the results of those problems with Pythagorean Theorem and the right triangle to introduce a new concept called related rates that says, well, simply because something is going to change one way in one part of the figure doesn't mean it's going to change the same way in the other part of the figure. And a lot of students, when initially presented with this kind of problem, if the bottom of the stick moves out at 1 centimeter per second, then a lot of students are going to think that the top of the stick also moves down the wall at the same rate, at also 1 centimeter per second, or per 10 seconds. And we could clearly see in the data that we collected that was not the case. Hence the concept of related rates. But again, I hope you guys were able to get something out of doing this activity. And if you have any questions about anything that you saw in the video or in the activity itself, by all means, please let me know. And until next time, guys, thanks for watching. Take care and be good.